Okay, I believe we're streaming now. So I want to start with a simple scenario to motivate our discussion today. You know me, I love this weird piece of equipment that I keep bringing up all the time. Oh, and let me pause this over here. There we go. All right, so just so you could see this a little better, let's put this whiteboard near it. Okay, so this is just basically a pendulum at this point. All right, sorry, that's a little crooked there. Sitting on something funny. All right, whatever. We're going with it. All right, so now I want you to think about something. Let's say I lift this thing here and I'm just going to release this thing from rest. One way we could attack this thing is we could figure out the torque. We know the moment of inertia, or we could figure that out in theory if we took some measurements. So we could get some lengths. We know where the pivot point is. We know some masses if we put this thing on a balance. So in theory, we could try to figure out the moment of inertia of this. We know where all the gravitational forces act, so we could get a torque. Now, what I'm curious about is the torque going to change as this rotates? What do you think? So compare the torque right here to the torque down here. Is it the same? Is it larger or smaller in one of those locations? What do you think?
I'd say it changes.
Okay, so as it moves downwards, what happens? Is it increasing or decreasing in your opinion?
We'll see the angle between mg, which is the force, and the distance.
So let's
the
start
radius.
right. Yeah, what's the angle between them right here?
90 degrees.
And then how about down here? What's it approximately, or what's it close to?
Like 10 or 15.
Yeah, small. Right here, what is the angle between mg and the r vector?
0.
0. So it starts out at 90, 80, 70, 60, 50, or whoops, yeah, sorry, yeah, but basically 90, 45, about 10, and then all the way down to 0. So how much torque is the gravitational force exerting at this point? A lot or none or some?
None.
None. We see it not rotating. Whereas here, it takes it from not rotating and it changes it. All right. So what is the point of all this? Is the angular acceleration constant as this thing falls down? What do you think?
Well, if the force is changing, then that means
the force is not changing.
That's true.
Mg is constant.
That's true. Okay.
The torque changing.
Yes.
Do you see the difference in those sentences?
Mm-hmm.
So the force is always mg acting at the center of the mass. That is basically always straight down with magnitude mg. The torque is changing because the angle changes as this is pivoted. Okay, so the torque is changing. Does angular acceleration change?
I would still say yes.
Yeah. Does moment of inertia change?
No.
No, the pivot point isn't changing. The location of the masses relative to the pivot point is not changing. So we see that the moment of inertia remains constant. As torque changes, angular acceleration changes. Would this be a good problem to use kinematics? If we wanted to analyze the speed of this pendulum as it swings?
No.
No, because it's not constant acceleration. Now, you could do it if you chopped it up into tiny enough segments in a computer code, and we will do that in a week. But so, yeah, this motivates sometimes, instead of handling this problem with torque methods, we might want to know another trick, energy methods. And that is where I want to start today. So let me just start with this share here. This is the big picture all day long. Okay, one method of solving problems could be sum of torques equals I alpha. We also know kinematics, delta theta equals, obviously there are other kinematics equations as well, but I'm just going to cheat with that one. Or we could do a new one. We could say K initial plus U initial plus work external and non-conservative equals K final plus U final. We could use these different tricks to analyze things that rotate and learn something about them. That's the big picture of today's lecture. Now, what's different is before, I'm just going to, obviously the potential term is usually mgh of some kind. And sometimes it could be 1/2 kx squared for a spring or something. But let's focus more on the kinetic. Previously, what was the way we wrote kinetic energy for objects that were translating around? Do you remember the formula?
1/2 mv squared.
What is the rotational equivalent of that?
1/2 moment of inertia omega squared.
Yes. Now, I just want you to watch out for this. There are some problems where we have it translating and we use this term, but not that one. There are other problems where the thing is swinging and rotating and we use this term, but not that term. Then there are a third class of problems, rolling motion usually, where we have both terms involved because something is rotating and translating as it rolls. So now obviously the same kind of thing would be here as well. You'd have potentially two terms of kinetic energy. All right. So far, so good on that. All right. Now, let's take a look at, where do I want to go with? Let's look at page 73, and I'll try and do a screen share. Give me just a second. I think I said page 73. There we go. So it's nearly identical to chapter 8 with a new rotational kinetic energy term. Now, there's different types. So this is the one we were just looking at, swinging motion. So let's look at some of these issues here. These are some of the standard issues that you face in an energy problem with swinging motion. So let's look at it. I want to point out something. Earlier in the semester, we talked about simple pendulums. Now, if you don't know what a simple pendulum is, that's a point mass on the end of a massless string. For that particular problem, it was okay to treat it with translational motion. In short, but basically, for anything other than a mass on the end of the string, it's better to use I omega squared than mv squared, okay? And there's a 1/2 on that. So again, earlier in the semester, I was not lying to you. We could model these problems that had a simple pendulum, a ball on the end of a string. You could model that as translational motion exactly. Where this gets tricky is if you have a rod with a mass on it or something other than a point mass on the end of a string. Then we need to use this new equation. So instead of 1/2 mv squared, where v was the speed of a ball at the end of a string, now we have to take into account the entire rotational mass. So we get a 1/2 I omega squared. Here's the issues. Gravitational energy, you have to figure it out from the height of the center of mass. If you're swinging, I don't know if you remember this from chapter 8, the height of the center of mass, you get this 1 minus cosine. Do you remember that from chapter 8? If I could, let me get my Zoom controls up here. Remember these triangles we made back in chapter 8? Whoops, that's bad. Right? The idea was this was the height right inside of that little tiny bit. And that is the height that the center of mass changes. And so we said, oh, this is the radius of the center of mass. And that's how we got this term right here. If you need help with that, we could talk about it more later. But basically, that was derived in chapter 8. So we see that happens again. Now, while not always true, typically the work non-conservative term goes to 0. Not always, but usually. And for this class, I'll try to make sure it's usually 0. Now, you could have axial friction, and that's how that might show up. If you had axial friction, that would show up in there. So a simple problem you could imagine is you give everything except for the work non-conservative and say, figure out the work done by the axial friction. So if I give you everything else in the problem, I think you'd agree it would be pretty easy to figure out what the axial friction is. Think about this. Generally speaking, that's very difficult to measure. However, we could easily measure masses and heights. You could use video capture analysis to get omega. We could calculate the moment of inertia. So it seems totally reasonable that you might be able to figure out all of this stuff, and then you could figure out how much friction isn't present in your pulley or your pivot or whatever. All right. Forces towards the center of circular motion do no work. Remember that. That's sort of like, remember how the normal force rarely did work because usually the normal force was perpendicular to displacement? Not always. And finally, check this out carefully. Translational velocity of any point on the object in circular motion is V equals R omega. So for example, if I wanted to know the velocity of this point, V, I would need its radius, R, and then I could say V is equal to that radius times the rotation rate, omega. And so if you want, a lot of times questions ask this, like for example, look at 10.48a. What is the speed of the end of the rod? That's basically saying what is V, not omega. It's saying what is V for the end of the rod, the part that's maybe going to hit me in the face if I get too close to this thing. I need the speed of that part. Okay. Questions on this while we've got it up?
So you would use energy to calculate omega and then use that to figure out velocity.
Absolutely. Standard technique. Let's go ahead and do this one. And rather than do the complicated one that I'm showing up top where you've got, let's just start with a simple pendulum here. I should be careful. Simple pendulum means ball on the end of a string. Let's start with a rod pendulum. So this basic pendulum right here, okay? So 10.48, I'm going to get this drawn up. You can read it. It's very similar to what we were just looking at. Theta 10.48. We're given mass and length L and theta and released from rest. Okay. All right. So here's the question. Part A says, whoops, speed of end of rod at lowest point in swing. Okay. So now just to kind of squeeze in both diagrams here. Usually, when we do an energy problem, we have a before and an after picture, right? So in this case, the red is going to be the after picture. And I'm going to draw a curved arrow like this to indicate that there's some final rotation rate. I'll call that omega final. Now we know initially We know omega initial equals 0 because it was released from rest. That's what gives us that piece of information. Released from rest tells us that omega initial is 0. I'm just going to go ahead and start writing and work this one out, but at any time, interrupt me if I'm confusing you, okay? So if you don't understand or wonder where I got something, just shout out, all right? So I'm going to start with K initial plus U initial plus work external non-conservative equals K final plus U final. In a great many of these problems, work is equal to 0. So let's verify that. There's forces at the pivot point. Do those do work? And if not, why not?
No,
we have
because the length from the pivot point is negligible.
Yeah, displacement is negligible. Did it say there was any friction here? It says there's negligible axial friction too. So we don't have to worry about friction doing work. Now, what about the molecules inside the rod itself? As it swings, they're generally exerting forces along the length of the rod, right? That's towards the center of the circle. Those don't do any work either. So if you're worried about, well, wait, don't I need some forces, some molecular forces to hold this thing together? You do, but those are doing no work. Air resistance. In real life, it matters. However, for this problem, let's ignore it. So that's what goes through my brain to say it's okay to set the work to 0. All right. Now, I next think, should I view this as rotational motion or translational? Well, it's swinging. Swinging motion is pure rotation. So what should I write for kinetic energy? 1/2 mv squared or 1/2 I omega squared?
I omega.
Yeah, and in particular, what is true about the initial kinetic energy?
Would it be 0?
It's 0 because it's released from rest, omega. So, all right. Now, over here, that would be there we go. All right. Now, what about U? What type of potential energy do we have here?
Gravitational.
Mm-hmm. When we do gravitational potential energy, what's one of the things we usually have to think about right away?
Setting the 0
Setting the 0. Where do you want to put the reference level 0 level?
at the bottom.
No, you could.
Okay.
Where do we reference the height in a swinging motion problem? Is it at the bottom? Is it at the top?
Oh, okay. So you mean the center of mass?
Let's put it at the center of mass at its lowest point in the swing. So that would be, this is a uniform rod, unless we are told otherwise. So I'm going to say right there. Let's say this is the center of mass. Let's say that is height. Center of mass equals 0. That's where I would put the reference level. Does that make sense why it's a little different this time? You good with that, Esteban?
Yeah, so it's the center of mass because that's where the force is applied, right?
That's right. That's where the gravitational force acts. So rather than having to do a bunch of calculus to figure out, oh, well, this part has a different change in gravitational potential energy than that part. Do you agree?
Yeah.
Every point on the rod has a different change in gravitational potential energy. So what we do is we reference the center of mass. So we only have to do one change of height rather than an infinite number. That's kind of convenient. All right. Is that good on that?
Yeah.
So notice that this distance right here is going to be height, center of mass initial. I'm going to call this other one height, center, mass final, okay? So let me I don't know if you can read that. It's getting sloppy here. So we need to figure out that little height. Well, what's this length right here?
L/2.
So what's this height?
L/2 1 minus cosine.
Yep. So height, center of mass initial is equal to L/2 times 1 minus cosine theta. That's the initial height. And what's the final height then? That term drops out. So I'm going to pause there. That's a lot of stuff. And this is about as simple a rotation problem as you can get with energy. So let's take a second, ask any questions you want, or, even if it's just like, I think this is whatever you want, any questions.
So the only thing we solved so far is just H.
Well, yeah. Yep.
Okay. All right.
Now, you get faster at this if you practice and it becomes a system. But if you don't practice, these problems have about 10 steps. So you need to just practice and get the 10 steps down. You're like, find the center mass. What's the next step, Esteban? Or anybody? What's the next thing you would find? And I guess we should be careful, Esteban. We found a lot more than just the height. We found many things that are equal to 0, which helps a lot. So that actually is most of it. But yeah, what's the next thing?
I guess we would make an equation, mgh equals 1/2 omega. All right. Oh, we have to find a moment of inertia.
That's what I would have done next. So before we bother plugging all that crap in, let's get what I is. What is I in this case?
Half ml squared.
No. It's not 1/2.
Half.
One third.
Oh, yeah.
It's 1/12 at the center, but we're at the
1/3.
end. So it's 1/3. Oh, and maybe, so now I want to point out one of the most commonly screwed up things on test days. Okay, here it is right here. The energy equation has a 1/2 in it. The moment of inertia usually has another fraction in it. So don't forget, you usually have 1/2 times 1/3. One of the most common things people forget is with a disk, because you get a 1/2 here and a 1/2 there, here a half, there a half, everywhere a half. Oh my gosh, what is going on with my brain? Anyways, so, and I'm not sure who was speaking up, but that might have been what you were thinking about, right? The half here and the... But
yeah, I got a little mixed up.
yeah, so that's the most common mistake. People do it all the time. Watch out for that. All right. So now we'll do what Esteban was recommending before, which is write out this crap. So we're going to get an M, G, H center mass initial, plus 0. These two are 0. So this is the U initial term right there. And then all this is going to equal, this is what I do every time. I write the half, then I put parentheses and shove in the moment of inertia so I don't forget the two fractions. You do it your own way, whatever makes you happy. And then omega final squared. Sorry, there's some glare. We are looking good. And now you proceed to solve for some crap. Ooh, what drops out? Maybe I'll plug this in so it's a little easier to see. I'm going to plug this in. Do you see anything that drops out?
The 1/2?
Oh, yeah. That's cool. I hadn't even noticed that yet. You're absolutely right. The 1/2 ends up dropping out. After all that talk about it, in this particular problem, the half drops out. What else?
The M.
M. What else?
L's drop, but 1 remains.
Yeah, one of the L's drops. What might be a good thing to do at this moment before you do a bunch of math? Check the
Units.
units. What do we have on this side? What are the units left?
Meters over second squared.
Yeah, meters per second squared, because this has no units. What do we have here? What are the units of omega?
1/2.
Yeah, or radians per second squared. The radians get absorbed into any other units. They're dimensionless. So it's looking pretty good. The rest is easy. Let's check it and see if there's something I forgot that I wanted to tell you in the solution, all right? It seems intimidating because that's like the simplest problem ever. But your first problem is always pretty hard, right? So let me see. What was this one? 10.48, I think. Okay, so there we go. So notice we had to get the L over 2 because we have to think about center of mass. We have this weird triangle here that we have to remember. So that's 2 things. We had to ignore the work done. That's 3 things. And then we had to get the moment of inertia. That's 4 things. And then do some out. So this one only had about 5 steps. Now keep in mind, here we get omega final. That's the rotational speed at the lowest point in the swing. The tip of the rod is distance L from the pivot. So look at this sentence right here. Let me just pause and make sure you understand it. I'm going to shut up, eat some Pop-Tart, live the dream here. You tell me if you understand this. What do you think? Is that making some sense?
Yeah, every point on the rod has the same omega, so
Correct. Every point on the rod has the same omega. Every point on the rod has a different V. Agreed?
yeah.
Yeah. All right. So let's go back and see what we got now. Did we do, that's part A. Okay. Does it make sense if theta goes to 0? First, what should the answer be if theta was 0?
0.
Let's go look at it. Do you get 0?
Yeah.
If you plug in theta equals 0, cosine of 0 is 1. We get no. Okay, so there's another way you could check your work, not just checking the units. Obviously, we could check the units too, but we just did that a minute ago. So I'm going to assume we did that right. At the lowest point in the swing, which way does acceleration of the end of the rod point? Oh, whoops. I skipped part C, but yeah, let's do part D. At the lowest point in the swing, which way does the acceleration of the rod point?
Towards the pivot point?
It's talking about ATAN, or is it talking
It's-
about
What? Yeah, so this is, if I said acceleration with no other disclaimers, what do I probably mean?
ATAN?
A total.
Oh, a total.
That's if the default is, if you don't specify, speed is translational speed, acceleration is a total.
Okay.
But what is, okay, so somebody said the correct answer already. It's straight up. So think about it. Where'd that pivot point go? Here it is. Whoops. Okay. Let's just get me in front of here. I'll be the background this time. So in this case, when it's swinging downwards, right at the bottom of the swing, let's just move this piece of brass up. Just pretend the piece of brass is the end, all right? So as it's swinging right there, we expect that right at this point, it's not speeding up, it's not slowing down, right? Just before it was speeding up, just after it's going to slow down. So right at the bottom, the speed is not changing. That means A tan is actually equal to 0 at the bottom. And AC is straight up. So that's why it points straight up. Is that cool? How about when you release it? Right at the instant you release it, which way is the acceleration pointing? Just after I let go of it. Yeah, this way, because there's no velocity, so there's no AC. And so it's all changed. Remember that crap? All right. That's what those 2 questions were about. So again, just after the release, there's essentially 0 omega. And as a result, if there's no omega, AC equals 0. It's all A tan. At the bottom, there's no A tan. All right, so you could plug in numbers. Ooh, how about this? Let's ask about this one. Okay. Let's say we have to figure out the translational speed of the tip of the rod at the bottom of the swing. Do you think it should be bigger, smaller, or equal to square root of 2Lg? Now, let me explain where that number comes from. If you just have a ball here and you drop it one distance L, you know that the speed before impact, I'm assuming you know this by now over and over and over, 1/2 mv squared equals mgh, you get the square root of 2gl. So if you just drop a ball from rest some height L above the ground, the speed just before impact is square root of 2gl. So now what I'm saying is, instead of doing that, let's say we put a pivot right here. And then I let this thing swing down to this spot. Right? Do you think the speed of the end of this should be equal to, less than, or greater than square root of 2gl? Which do you think is faster, a ball falling straight down or the end of the pendulum swinging down? Got the question now? What do you think?
The bottom of the pendulum?
Okay, what's your reasoning?
Well, I was just kind of comparing the two, and like the ball goes straight down. So it's like all the force of gravity is just pushing down on it.
Okay.
Whereas with the pendulum, if you're releasing it from rest, it kind of starts off slowly because it's only a portion of the gravitational force acting on that direction. So as it goes to the bottom, it's kind of speeding up.
Okay. Well, let me ask you this. How many forces act on the ball when you drop it?
Just mg?
Yeah, free fall, right? How many forces act on the pendulum?
Part of mg, then it's possibly friction if it has any.
There was no friction at the pivot.
Oh. Then the acentripetal, or the force.
That's an acceleration, not a
yeah.
force. When you think about forces, think about objects. Mg is caused by the Earth. The Earth is pulling down on there. Is there another object that exerts a force on the rod?
Pivot.
The pivot. Which way does the pivot exert a force, if you had to guess?
Up. And
Okay, so there's a force from the pivot. I'm going to label that force R, just because that's commonplace in chapter 12. What do you think that's going to do to the acceleration if there's a force upwards?
It's going to slow it down?
Yeah. However, your original answer was correct. This is very complicated, it turns out. The center of mass will actually have a smaller speed than this, whereas the tip of the rod, I don't know if you remember that faster than G crap we talked about a little bit in the last class, where something right around 2/3 of the length of the pendulum is the over under for when you get acceleration greater than G. So most of the rod accelerates less than free fall. All right, whatever. But if you wanted to learn, what you could do is do the math, or whoops, oh crap. Let me get into here. If we scroll down, there we go. This is just like the pennies on the meter stick. So the end of the rod actually goes faster. However, if we look at the center of mass, it turns out it's smaller. So the center of mass actually falls less rapidly, whereas the end of the rod falls more rapidly. Oh my gosh, that's crazy. All right. And then, whoops. Yeah, I mean, just looking at this, here's the idea. Look at this pivot point right here, this shiny piece of metal. When you drop this thing, the pendulum doesn't fall to the ground, right? Clearly, it's exerting an upwards force. Now, it may also exert sideways forces or something some points, but yeah, all right. That's that first problem. What do you think? There's a lot to learn in that one. You may want to reread that one. There's a lot of conceptual knowledge to be gained there. All right, let's take a look here. Where are we? Whoops, this one. All right. You take a look at 10.49. I believe I have this video here, but I got to bring it up. So give me just a second. Okay, I found the video. What do you think? Any guesses? Basically, you have one that's a full meter stick and one that's a half meter stick. Which one's going to get down to the bottom first? Or is it the same? What's your gut tell you?
The smaller one.
Okay. Let's take a look here. Somebody's in the chat there. Okay. So when we run this one, the videos that my students edit always look better than mine. Clearly, the shorter pendulum actually oscillates faster. You could just see it there. It's not even close after one full oscillation. All right. And so you could, whoops, we don't want that one right now. Let's do this. So if you think about this, let's actually look at the equation we got, right? When you look at this omega right here, this is the best way to see it. The object with the larger omega should have a shorter L. Think about it. If L is in the basement here, the shorter L is, the more omega you have. The more omega you have, the faster you get to the bottom. And so notice that when we're talking about this race, thinking about velocity is confusing. It's easier to think about angular velocity because these two objects, if you want to compare two different length objects as they rotate, RPMs is a better way to compare speed. Angular velocity is a better way. So that's what that was supposed to be about. That was it. All right, so that's cool. All right, let's keep going here. So now this is a good one for you to do at home, or 10.51. This is very similar to the last problem, except what's going to be a little bit uglier in this problem?
Your center of mass changes and also your moment of inertia.
And that's it in a nutshell. That's how these problems differ every time. You get a different center of mass and a different moment of inertia. Maybe you have a different starting angle or length or something, but whatever. Now, look at this one. This one, actually, I really like. So if you're looking for one challenge or something, I think these ones are probably some of the more bearable challenges in the book. So if you don't usually do them and want to push yourself a little bit, that's the way to go. But let's look at it really quick. So notice mass M. Let me underline this a little bit. Point mass M is attached to the rod distance X from the pivot. So that is distance X. My question is, which value of X do you think is going to give the maximum rotation rate? Do you think X should equal L, Should it equal 0 or should it be something in between? Obviously, you can't really discuss with your neighbor. Well, you could try in the chat. Which value do you think is going to give you the largest rotation rate at the bottom?
Well, if the ball was all the way to the end, I would assume that would give you a bigger moment of inertia. So therefore, you have bigger angular acceleration.
Wait, if you increase moment of inertia, what happens to alpha?
Oh, you're right. You're right.
However, if you stick the mass all the way out at the end, do you get more or less torque?
More torque.
So you get more moment of inertia, but you also get more torque. Is it obvious what happens to alpha?
I guess not.
Yeah.
That's interesting.
It is, isn't it? That's why I'm like, this is one of the few that's actually pretty interesting.
But on a pendulum, when you push out the mass, doesn't it swing faster? Like that pendulum you have behind you?
So in this case, let's find out. I'm going to erase this so the board is cleaner to see it. Okay, so Esteban's asking a simple question. Which is going to swing faster? When the mass is close to it or when the mass is far from the pivot, right? So in this case, here's far from it. And I got to step on this thing, put some weight on it. Okay. Versus putting it close. Which swings faster?
So close.
Yeah. So based on now, yeah. All right. So why do you think that is? You get less torque. We are getting less torque. We are also getting less moment of inertia. Which one is affected more by the position? And why? What's the moment of inertia of a point mass?
The mx squared.
What's the equation for the torque? mx sine theta. Which one is more affected by position?
The torque.
The moment of inertia.
Moment of inertia, yeah.
Squared.
Yeah.
So this is one of those trade. It's not that they're not both. So if you increase x, you get much more torque, but you get much more moment of inertia squared. So you get much more resistance to that torque causing angular acceleration. So based off that, what do you think the answer to this challenge is? What value of x gives the maximum rotation rate, if you had to guess? For part D.
0.
You would think that, but it's not 0 either, because the rod has some mass itself, and so it actually helps to have it right about here. Isn't that? It's something in between. It's not 0, it's not L, and so in fact, what we learn from this one is sometimes you just got to do the math, and there's no way to guess. I didn't know the answer. I did the math, and when you do it, okay. So clearly, look at this question 10.49. You better read this one at home. I did a lot of concepts on this, okay? So you better read the answer to that later. But when we look at this one, that's what it looks like. It turns out it's almost a constant value of about 5.5, no matter what value you choose. But so for this particular set of masses, you could take the derivative of this thing with respect to x and figure out where the maximum is. And notice it happened for this particular rod at about 0.0264 meters. And you could see that it's almost the same no matter where you put the mass. Look, they're all pretty darn close. They're all within about 10% of each other until you get way out to here. Isn't that weird? There's just no way around it until you do the math. Now look at this math. It looks scary, but it's all the same junk we've been doing all along. Notice here's how you get the center of mass distance. There you go. And then once you get that, then you just plug in the center of mass radius into this equation, just like always. The moment of inertia, I've got a 1/3 ml squared from the rod plus an mx squared of the point mass. It's 1/3 because the pivot is at the end of the rod, not the middle of the rod. And the math is pretty much the same. It's just slightly uglier. So these problems do not look pretty. So you have to practice to get used to the ugliness. And then after a while, it's just like, nah, it's big and it's ugly, but it's not that hard. Any one step is easy, but there's a lot of steps you got to practice. All right. Questions on that before we fly past?
Are you going to throw any non-uniform rods at us?
Oh, we could do that. That would be a very easy problem to mix it up. What would be different if I had a non-uniform rod? I probably wouldn't put a point mass. It would look like this one. What would be different, Esteban? If you had a non-uniform rod?
Your center of mass, you have to calculate the center of
You
mass.
calculate the center of mass with an integral, and you calculate the moment of inertia with an integral. And then it's exactly the same problem, right?
Mm-hmm.
So, yeah. Generally speaking, I don't tend to do that, but do you agree it's not that hard? Oh, well, I should be careful. Do you agree it's not that different once you know that trick? It's always get the center of mass, get the moment of inertia, shove it into this equation. That's pretty much it. Get the moment of inertia, get the center of mass, shove it in. All right. Yeah, that's for swinging motion, the easiest problem. Yep. Okay. That doesn't mean it's not going to take you some time, so you better practice. What about 10.51? Does this problem make sense, or is it rotating the wrong way? Did I draw the picture backwards? So we're looking at 1051, and it says, think, explain why the disk with the hole rotates as shown. That's actually correct. Can you explain to me why that kind of makes sense?
Because there's more mass on the left than on the right.
So where is the center of mass in the initial picture?
More towards the left.
Would you say it's probably right about there, maybe, or something?
Mm-hmm.
And so then here, it's always going to be right on that line about the same distance away. So this is very similar to the last problem, except it starts horizontal and ends up at an angle. You've got to do a center of mass calculation with a hole in it. Okay. You also need to do an angle, but this time the angle is from the horizontal. In the previous problems, the angle was to the vertical. So this is probably going to switch all your sines and cosines, because the angle from the vertical now is 90 minus theta, right? So basically, these are the tricks that you got to watch out for. Where is the angle drawn? How do you get the center of mass? How do you get the moment of inertia of this thing? How would you get the moment of inertia of this? Do you remember?
So it would be moment of inertia. It's just a disk, right?
Yeah.
Of the disk, and then minus the moment of inertia of the hole.
Yeah.
But then you gotta change it by md squared because it's not centered, right? Or no?
Yes.
Yeah.
Good catch. So notice the center of mass is right there. So notice once we, excuse me. So this one right here, now if we figure this out, if we do this one about the center, this is the one that I would probably shift the hole, right?
Right.
And so that will end up shifting the total to this new spot. So, oh man, yeah. So you've got some work to do on these problems. Now they're messy. All right, let's leave it at that. You could do that at home. All right. Now I want to level. Okay, so you could look at that one at home. I want to look at this next one. So in this case, this is a new type of problem where you have one object spinning, say a pulley, and two objects translating, say these hanging blocks. Okay, so now let's look at these things. If we were going to do an energy problem, let's think about this. The pulley doesn't move up and down, so I don't need to worry about gravitational potential energy or translational kinetic energy. Does this first bullet point, well, I'm just going to go through them. You ask anytime you want. So the pulley's not moving up and down. I don't worry about mgh or 1/2 mv squared for the pulley. The blocks are not rotating. So I don't need to worry about 1/2 I omega squared for those. I just have to worry about 1/2 mv squareds, right? So these have 1/2 mv squareds, and they also have mghs, right? This one just has a 1/2 I omega squared. All right. Now, tension is an internal force. Tension does no net work. So this is a great way to use an energy problem, because otherwise we got to do free body diagrams and all kinds of stuff, and we will show that. But the tension on these does no net work. Okay, we're going to assume axial friction is negligible unless otherwise mentioned, okay? Otherwise, you stick it in that non-con. So again, we're going to ignore axial friction pretty much all the time. And now, why is this problem really challenging? The arc length of string unraveled from the pulley is equal to the height displaced by the blocks. Okay, so what I'm saying is, if this one falls, let me get a dark red here. Let's say this one falls some distance h2. That means distance h2 of the string gets unraveled from that one. Let me just draw that. So this is length h2, which is equal to r2 times theta, the angle through which it rotates. Does that make sense? That's the arc length traveled by the string of the second block.
Why'd you put a subscript on the R?
Well, look at the purple block. Is it the same?
No. Oh, okay. I guess because there's two different circles.
And now we
Okay.
see the horribleness of this problem.
Yeah. Okay.
Now look at this. Do you see they both rotate by about half of a circle there? Let me try and make this look. So let's say this thing falls by half a circle, or it rotates 180 degrees. If the pulley rotates 180 degrees, the purple block is on, whoa, shoot, wrong color. The purple block, or number one over here, is only going to move up a couple of centimeters. Whereas the red block is going to fall down many centimeters. And so we see the angle, they both rotate 180 degrees, but H1 is equal to radius 1 times theta. It's a different arc length. Ugh. Is that good on that? And I think I saw, oh, sorry, this button here. There we go. Gnarly, gnarly, gnarly. It's actually, any one step is really easy, except there's a lot of steps and a lot of details to pay attention to. In previous pulley problems, we didn't ever have to talk about the radii of the pulley. Now that matters because the radius of the pulley relates to these. Now look at this. Are these blocks going to move at the same speed?
They have the same omega.
They have the same omega, but is that the same speed?
No.
No, they have the same angular speed, but V1 final is equal to radius 1 times omega final. And the other velocity uses radius 2. So notice blocks don't have the same speed anymore. Ugh. It's not that hard but it's time consuming. And so you have to practice it and get faster at it, or these types of problems will kill you. And I love to throw one of these somewhere on the final just to see who did the practice and who sucks. All right. So not lying to you here. Just make sure you're good at multi-radius problems. All right. So not trying to, it's just practice. It's not that hard, but you do have to practice it. And that is going to be tedious. Just giving you a heads up. All right. Any questions about all this junk that I have on the screen? Let's take a look at whatever I have down below here. So again, this is a problem where a pulley spins. It's got rotational energy. And what should I have said here? That's a typo. The blocks are
translates.
translating. Yeah, I don't know why I said rotate, but yeah, I said it correctly down below, but I, for some reason, screwed it up in the title. Let me put a note to myself. Where's my pen? Come on, pen. Sorry about that. Okay. And let's see if there's anything else down here. I think we've covered this. All right. So the most important bullet point is that thing. When the strings connect to different radii, the displacements of the blocks are not equal. Now, let's start with the simple one where there's only one radius. Okay. So page 76, let's start with this simple one. These were the answers we got in chapter 5, I believe. Okay. And what we want to do is show that this thing changes. So let me just show you how to do this. 10.52. And we're going to start with torque methods. And then I'm going to redo it with energy methods to show you both ways. Okay. So we could do torque. We could do energy. Let's show how you could analyze this problem. So I already forgot the problem number, 1052, I think, right? 10.52. I think I had drawn a red block over here and a purple block over here. Okay. Now, so this obviously isn't perfect. And let me make sure I write these masses correctly. Okay, 1. Left log is purple. Okay, yeah, 1. Okay. Now I'm kind of running out of room here. Maybe I should draw this a little bit higher up. That's the pulley here. Okay. So here I have M1G. What's the force pulling upwards on this block?
Tension.
Okay. And is that going to be the same as this tension? It's the same string. What do you think?
Wait. I'm second guessing myself. I'm pretty sure it's no.
You are correct. It's not the same tension anymore. What was the requirement in chapter 5 to say they had the same tension?
Massless pulley.
Yeah, is that true anymore?
Nope.
No, now our pulley's got some moment of inertia. And here's the idea. Think about it. If these two tensions are the same and this pulley has some mass, it shouldn't ever rotate, right? Because it would take energy to rotate it or torque to rotate it. If these two strings have the same tension, There would be no torque. It wouldn't spin. So the only plausible scenario is the tensions are no longer the same. And in fact, they were never the same. They were always close enough to the same we could ignore the difference. So in chapter 5, if the pulley has negligible mass, these two tensions are, for all intents and purposes, identical. But in reality, this one was always a little bit larger than that one. Otherwise, it wouldn't make it rotate that way. All right. So now, these are the forces acting on this one. Which way is this one going to go? Let's assume 2 is heavier. So this one, let's just assume this one goes up. And this one is going to accelerate down. So I'll call this A and this A. So do you think these accelerations are going to be the same? Or do you think they'll be different?
Well, since tension's different, then acceleration has to be different.
No, they're the same
No?
still. They're connected by the same string, which is not stretching. So if one of them moves 1 foot, the other one has to move 1 foot as well.
Okay, that makes sense.
So the accelerations are still identical because they're still linked by a non-stretchy string. Now, if you hook these up with a bungee cord, then they would be different. So that's what's unique about this. The tensions are no longer equal, but the accelerations are still equal. Ah! All right. Next. Isn't this fun? All right. What are the forces? Now, careful. What did I say? I didn't say torques. I said, what are the forces acting on this pulley? Give me one of them.
MG down.
MG down. Where does that act?
Center.
At the center. Okay, and I'll just call this mass of the pulley times G, okay? Are there any other forces acting on the pulley?
R force.
Yes, we call that the reaction force, absolutely. And that's going to be at the center. That's holding the pulley up. Otherwise, it falls down. Right? That's like this thing, right? The pivot point has to keep this from dropping to the ground. That's the R force. All right. The reaction force. What else we got?
And then you got 2 tensions.
Yes. Tension acts down this way. And now here's the thing that's a little bit weird about this. In reality, the string is actually exerting a frictional force on the pulley. However, that frictional force is equivalent to these 2 tensions. Think about it. If there was no friction, like this, give me a string, give me a string. Where's my string? Here's a weird string. Face mask. All right. This is, you could tell we're in different times. All right. But like this. So imagine if this has negligible friction here, then the string would just slide over it and the pulley wouldn't turn, right? So there is friction between the pulley and the actual string here. So weird. This is one of my weirder demos I've ever used, right? And the idea is if there's, and now it's a white background too. It's like you can't see anything, but yeah. You can't see this at all. Sorry. This horrible demo. So I'm stopping. But the idea there is effectively friction is what keeps the string from slipping on the edge. So we need friction on the edge of the pulley between the string and the pulley itself. But we don't want friction at the axle because that causes a torque that slows it down. End of the story is we're going to assume there's 2 tensions acting on it. That's it. Got it? So if you need to know more about that, you could talk to me later, and it's very subtle. All right. We're going to assume that the string does not slip, and that's what allows us to say tension 1 and tension 2 act on this one. All right. So now, out of all these, somebody just give me the force equation here for this block number 1. What's the force equation?
T1 minus M1G equals MA. M1A1, sorry.
M1A, because they're all the same acceleration. Somebody else, give me the force equation for this one.
T2 minus M2G equals M2A.
Not quite.
Oh, is it negative? Oh, okay.
Or you could have flipped, yeah, you could have said negative MA, but basically here, A is the positive direction usually. Remember what we did before? We generally said that way is positive.
Right, right.
So that makes this one positive and that one positive and this one negative. Again,
Yeah.
Is that cool?
Right, right.
Got
Yeah,
it?
that makes sense.
All right, got it. Now, let's look at this pulley up here. Which forces cause zero torque for this pulley? Right? We don't want to do forces on the pulley because it's not translating. The total force equals zero.
The R force and mg are
And yes, those
run
ones
through the
cause no,
center.
yeah, line of action through the pivot. All right. So then what is the torque equation for this one? Well, let's take a look. What's the distance from the center to the point where the force is applied?
Radius R.
Radius. And so let's call that radius little r. Is that okay?
Yeah.
And I think in the actual problem, I called it big R, but we already labeled it big R. So this is where we get a little confused here. But let's just call that little r. What's the angle?
90 degrees.
Yes. And this is something weird about pulleys that always is true. There's my other string. I found it finally. That old flashlight. This drives Juanita crazy, all this crap I leave laying around in this room. But I just want to point this out. I don't know if you could see it very well. I'm going to try my best. Okay. Whoops. Oh, this is like hitting the keyboard. So sorry if it does something weird. Okay. I don't know if you could see this at all, but no matter which way you do this, it's always coming off the string at a right angle, even up here. I don't know if you could see that at all. Whoops, I'm like smashing mass into something. But even right here, no matter where you connect the string, it's always going to separate from the pulley at a right angle. So that's one nice thing about these, because the torque always uses sine of 90 degrees, which is 1. All right, so don't worry, I haven't forgot about the break. It's coming soon. If I can try not to kill myself here. Smash my wall. So, based on that, what is the torque equation for this sucker? Let's remind ourselves. Sum of torques equals what? Not MA, but
IA or I alpha.
I alpha. Okay. We're going to have two torques. We're going to have torque 1 and torque 2. Now, these are vectors technically, but what we're going to do is pick a coordinate system. Which way do you want to call positive based on what we've done for this block and that block?
Clockwise?
Yes. Clockwise makes sense to call positive because we assume everything's rotating clockwise. So here's the case where instead of using the math direction, we're going to use the physics direction. So in this case, we're going to assume that direction is a positive rotation. Okay, so now which force causes a positive torque? T1 or T2?
P2.
So we should get something that looks like torque 2 minus torque 1 equals, what's the moment of inertia? Do we know? We don't. Let's just leave it at I. I don't think they told us. Okay. If it's a disk, it would be 1/2 mr squared. But I don't think we know it's a disk exactly. Maybe it's a sphere or something. Who knows? Maybe it's a basketball, whatever. And alpha, that's just alpha. So again, by choosing this rotation direction, that is what allows us to get rid of the vectors here. Technically, it's a vector equation. Because everything's rotating that way, I get rid of the plus minus sign, or get rid of the whatever you want to call that, k hat or negative k hat, however you want to think about it. What is torque 2? Well, that's force 2 times radius 2 times sine of theta 2. And then there's torque 1, radius 1, tension 1, and sine of theta 1. To be clear, I think I may have said torque here, but it's radius 2, force 2, angle 2. Radius 1, force 1, angle 1. Apologies if I misspoke earlier. I alpha. In this case, we've already discussed the angles are 90 degrees. In this case, the radii are the same. Now, I'm worried I'm going a little quickly here, so I'm going to pause. Is everybody okay with this equation? So you plug in 90 degrees for these two. You plug in little r for this one because they're the same. Here, what could I do to get rid of these tensions? Any ideas?
Use your force equations.
Force equations. You could grab tension 1 from this one and shove it in. You could grab tension 2 from this one and shove it in. Is there another way you could solve for this to figure out the acceleration? There's a trick. You could also, well, in this case, you could actually multiply these equations by r. Now, I know this seems weird, but if you multiply this by r, you get an RT1, and you could add those equations and the internals drop out. You can multiply this equation by r, and then that will drop out this term. Do you see it? Now, when you do that, this is the part I want you to pay attention to. A is not your alpha, it's R alpha. So you could change this to M R alpha times R, you get an MR squared alpha. Let's look at the solution, because I think the solution is worth, there's some nuggets in here, okay? It's all about being fast. You could do this problem in a million ways. You could also do it in the fastest possible way, so you spend less time on this and more time on stuff you care about in life. All right, so here's kind of some different ways of looking at it. Take a look, and after this problem, we're taking our break, okay? You guys have been troopers. Oops, let me get it just a little bit higher. Sorry, just trying to get the whole thing on the screen. Okay. Whatever, that's close enough. All right. There are many correct ways to do this. So basically, I like to stack the equations. In order to stack the equations, what you either have to take this equation and divide by r, or you could take these equations and multiply by r. Either one works. But so what I did is I divided by r to get units of force in this problem. In a different problem, when they have different radii, it might make sense to do the other way that I mentioned. So if you have different radii, multiplying this by r1 and multiplying that by r2 might make more sense. But stacking them and adding them makes short work of this. Got it? Questions?
So it seems like it changed the previous equation by just 1/r².
I over R
Oh,
squared.
I/r².
Which, think about that. Does this have the right units? What units should that term have?
Just kilograms.
Kilograms, but moments of inertia are always kilogram length squared, right?
Mm-hmm.
So that makes sense. Yeah, and now think about it. If the moment of inertia is small, this term drops out, agreed? If you have a small mass pulley, this term drops out. We get back the old answer we used to have. This is good. So what I was teaching you in chapter 5 was pretty good as long as the mass of the pulley was negligible compared to these other ones. And yeah, so that's totally reasonable. All right. You could also solve for the tensions. I did that. And again, we get the same results back when I goes to 0. So again, if mass 3 is 0, the moment of inertia is 0, we get back the same results. Woo! Oh my goodness. Oh, we need a break. Let's take our break and then we'll do this one and then we'll do rolling motion. Okay. So let's take our break. You gotta rest up for this one.
Are we going to do the energy portion of that other one, or?
Yeah, we'll come back and do the energy one next. But I think it's been an hour and 20 minutes of nonstop intense. So I think we should let's reconvene in 9 minutes. Okay. So am I going too fast for you all, or is this okay? I'm trying to slow play it. I'm deliberately slowing myself down. I hope I'm slowing myself down enough. It's about right-ish.
I think you're good.
Okay. It's pretty confusing stuff, so, and I just don't know what you guys don't know, so I'd rather go a little slow at some times at the risk of being boring than just kick your ass and leave you in the dust, right? So
It's just switching all the like equations together.
All right. So let's look at the next one now. I think we're at 1053. So wait a minute. Look at 1053. Let me make this a little bit smaller so we can see everything at once. Okay. So we're talking about this Atwood's machine. In the previous problem in 10.52, I said the tensions aren't equal, but I said that the accelerations were the same. And we said that the acceleration of this thing angularly relates to those two with the equation A equals R alpha. So to be clear, the pulley had an angular acceleration alpha because the string didn't slip relative to the surface. I know that the tangential acceleration of the string as it goes around here, which is equal to the translational acceleration of the blocks, is equivalent to R times alpha. However, is the acceleration A of each block, the acceleration magnitude, is it going to be a constant? What do you think?
I don't think so.
Do we have any equations we could use to guide our reasoning on how A should behave? Is G a constant? M2, M1. What about I and the radius? Is everything in that equation a constant? Sorry, you cut out there.
Yes.
It is a constant. And so the issue is this. Remember, if the pulley has mass, the tensions are different. If the string doesn't stretch, the accelerations are the same. If the string has no mass, the acceleration is constant because you have the same amount of mass on each side of the pulley. If this was a heavy chain, as you bring more and more mass to this side, M2 and M1 would effectively not be constant. M2 would be getting bigger if you used a heavy chain. M1 would be getting smaller if you used a heavy chain instead of a light, inextensible string. Again, we have a massless, inextensible string, so the blocks accelerate with equal magnitude at a constant rate. Woo! That said, couldn't we then use energy and kinematics to do this problem? Oh, we just answered part A. What assumptions do we make in order to assume the acceleration of the system is constant? Massless string. Sorry about that. I phrased it a little differently than I asked it there. So if you have a massless string, right, that's what gives us constant acceleration. Okay, so now in this case, if this one falls distance h, what's going to happen to block 1?
Should move up distance h.
Now, if they had different radii, would that be true?
No.
But it is true in this easy case. What about this thing? How much is this going to rotate?
H?
That's the arc length that it rotates has to equal h, which says that r times theta is equal to h. So we know how much it rotates angularly. Now, what about these blocks? This one's going to be moving downwards, right? With some speed v. Let's call it v2. Is v2 going to be bigger than, smaller than, or equal to the velocity of 1? When 1 gets up here, it's moving upwards with speed v1. Which one of those speeds should be bigger, v2 or v1?
Should be equal.
Equal. What is the key word that allows us to say they're moving at the same rate?
Well, they cover the same distance and they have the same acceleration.
Because the string is inextensible, right? If the string stretches, they could move different amounts. If the string is not stretching, they move the same amount. Good. So here, we don't even need V1 and V2. We could just call it V. How does that relate to the rotation rate up here? How does V relate to the rotation rate omega? It's not your omega.
R omega.
R omega. So it's a straight up energy problem. We've got two blocks. I would call this reference level 1. I would call this reference level 2. And then you could have them move. All right, so let's go take a look at the solutions and see. So here's what it looks like. So all initial speeds are 0. The two blocks are translating. The pulley's rotating. Block 1 moves upwards. I set its initial height to 0. Block 2 is moving downwards. I'm going to set its final height to 0. Okay, there's no net work. The tension between the purple block is internal. Tension between the red block and pulley is internal. Basically, both tensions cause no net work. It speeds up the blocks or slows down the pulleys. Slows down the pulley. Okay, and these two points are valid even though the tensions are not equal, right? Because T1 acts on the pulley and block 1 in opposite directions, etc. The forces acting at the pivot do no work because the pulley is not being displaced, right? It's rotating, but it's not displaced translationally. And so we get this ugly equation. Take a look at that. M1G_Y1 plus M2G_Y2. That's just the two initial gravitational energies. There's no initial rotational there because everything started from rest. Then I've got the final gravitationals. These are the translationals of the blocks, and here's the rotational. So now I put in the zeros. Y1 initial is 0, and Y2 final is 0. So that's why those two drop out. Notice here I dropped the subscripts 1 and 2 on the masses, on the speeds, because they are the same at the same radii. Now we could use this last result. This is the trick. If you forget this step, your answers never work out. So basically, you either have to convert the velocities to omegas or vice versa. In this case, I said, well, I've already got V's in here. Screw it. Let's just take this omega and replace it with V over R. So that's what I did right there. Notice you still have the moment of inertia and you have the 1/2 from the energy equation. So if you had another 1/2 in the moment of inertia, watch out for that one. All right, so you get this big ugly mess. So not a problem. From here, you could use kinematics, right? We know V initial is 0 for one of the blocks. We know V final is this big ugly mess, but when you square it, it's not quite as ugly. We know AY is what we're looking for. Delta Y is H or negative H, depending which block you're doing. But so for me, I assumed down was positive for M2. So I assumed delta Y was positive H and AY was greater than 0. You get the same answer as before. So I'm going to pause right there. Esteban, you had asked about this a little bit too. Does this kind of make sense to you?
Yeah, I'm trying to think which one seems easier.
This
I
one
feel.
seems easier to me.
Do you think so?
Well, I don't know. Well,
I don't know.
let me go into this. Sorry, I meant to go to a different screen. I've got a rule that might help you. Take a look. If we're asking about acceleration, typically that relates to force, right? Do a torque problem. If we're asking about speed, typically we do an energy problem. That's usually what makes me decide to do one over the other. If a test question asks me to get rotational speed or translational speed, I usually try energy methods first. If it asks me to get acceleration, usually I do torques and forces. Got it?
Okay, got it.
That's not a hard and fast rule. There are times you might choose another one. Now, to be clear, actually the energy method is probably a little bit harder because you have to do energy and kinematics. That's two problems to potentially screw up versus just one. But torque, you got to get the angles and the lever arms. So they're both, yeah. 6 of one, half a dozen of the other. They're really about the same. Cool. Now, watch out. I want to point out something very different about this problem versus the first one we did. Let me show it on the board just so I can give you an idea here. Okay. I think there's a huge fundamental difference between a swinging pendulum problem and this problem. So compare these two problems where this one's released from rest and then it's going to start rotating versus this one, maybe it starts rotating that way. Okay. What is maybe the biggest difference in your opinion? It's okay to be wrong. It's a very vague question and I know it, but there's a huge difference between this problem and that problem. In particular, what is a tool that we can use to analyze this problem that is not legit for analyzing this one? Maybe that clears it up. What technique?
Kinematics.
Kinematics works here, but kinematics doesn't work here. Why?
Because the acceleration is not constant.
Exactly. That's the big difference here. So this one, you almost always have to use energy. Got it? So I don't know how you're going to remember this other than write this down. Swinging objects, not constant acceleration. Write that 500 times and then you'll be good. All right. I see it so many times on a test. I give people this easy problem where it's just like do energy method for a swinging pendulum. And they practice torque so much. They do torque and they do kinematics, but it's not valid because angular acceleration is not constant for a swinging object like that. Watch out for that one. Okay. With the pulley, it's right symmetrically loaded about the pivot point. So yeah, anyways, that's why alpha, yeah, it's all right. Let's leave it at that. All right, here's one that's got a spring in it. You could do that by yourself. Here's one with different radii. Here's another one with different radii. So to be clear, the this page right here is good practice for your final, right? If you want to make sure you can handle these problems, do these because you learn what you don't know when the radii aren't the same. I have seen many students that are otherwise good at these just completely fail. Now, woof, this one will hurt you. But if you want to be good at this, I'm telling you, if you do this entire page, I suspect the hardest problem on the final exam will be easy for you. And if you don't, I suspect the hardest problem on the final exam will be impossible for you. Your call. And right, just doing one of them is probably not enough. But like you could see here, here's an energy method, here's a torque method. Right. And then one of these is this, I see acceleration. So that makes me think about forces and torques. And then this one, acceleration. So forces and torques. Now you might try it with an energy method just to try it both ways, even though, yeah. So just watch out, people. All right. Before we go on, any questions about that? It's not that you can't do it now. It's you'll be so slow and crappy at it if you don't practice it. It's not rocket science. It's just pulleys. Okay. All right. Next. Rolling motion. All right. Things get a little bit tricky here. And let me see if I have a... Let me do this one. Right here. Okay. I have a hoop and I have a wooden disc here. Let me make this full screen. Maybe. Okay. And then I'm going to slow it down just a little bit. All right. And so I'm going to release this thing. Okay. Forget about this. That's just showing you this is angled. So the ramp is not level. There's a small angle. In theory, we could calculate the angle, right? We'd know the length between the 2 feet. So in theory, you could figure out all this junk. All right. And so now what I'm going to try and do is I'm going to try and release them from rest. So you have a solid piece of wood, a solid disc, and you have a thin ring. So that's supposed to be, sorry, that's so crappy. We have a ring. All right. So that's, yeah. So which one's going to win the race? I'm going to release him from rest and let him roll downhill. Which one should win? What's your gut tell you? What factors might be involved? Take a second to think and respond. Go ahead.
I was going to say the ring.
And why?
It has more torque. All the mass is at the edge.
Where's the center of mass for a ring?
In the center.
Where's the center of mass for a disc?
The center.
Does that make sense with what you just said? Do they have different amounts of torque? What factor would affect the torque there?
The size of the radius.
They have the
Or-
same radius. They have the same exact radius. I don't know if you could see that. Sorry, I didn't say that. They have the
No, it's, I understood that.
Okay, my bad.
I don't know. Well, the inertia is different.
Okay. The inertia might be different. Do you think the mass is going to matter? If they don't have the same mass? What if I told you the ring was heavier? What if I told you the ring was lighter?
I guess I assumed that they were the same mass, just one was a ring and one was a disc.
It turns out they're not the same mass. They're very close to the same mass, but they're not exactly the same. Let's just run this one. Let's see what happens. Trying to make sure they don't bump into each other. Trying to make sure they're going straight down the track. Sorry, it's in slow-mo. Even though I let go of the ring first, the disc still beat it. Did you see that? I let go of the ring first by accident, despite my best efforts, and it still got beat by the disc. What about, let's try this one. How about this one? I have two spheres. They're both solid. I have two solid spheres. I'm releasing them. Their center of mass of each sphere is on the starting line. Which one's going to win the race if you had to guess? Obviously, the smaller one has less mass. You could assume they have the same density. Which one do you think should win this race?
The larger one?
Interesting. You think that's air you're breathing? What do you notice?
They're about the same.
Basically about the same within error. Let's see what this next one is. What is that? Oh, what am I doing? So now I'm going to do a sphere versus a cylinder with the same radius. I know this seems, after this one, I promise I'll stop. These ones, I believe, do have the same mass. What do you think? Who's going to win if you had to guess? Solid sphere versus solid cylinder.
Cylinder?
Interesting. All right. All right. There's a pattern here, and it's hard to observe. What's interesting is mass doesn't matter. Shape is the only thing that matters. Weird. So this is a very unusual phenomenon. We want to understand the underlying principle between all of these is the numerical factor that sits in the moment of inertia determines which one gets down the hill fastest. Isn't that crazy? I think it's crazy.
So
let's go ahead.
Less inertia will make it go faster, or opposite?
No. So here's the thing. The big cylinder and the small cylinder, the big cylinder had or the big sphere, I think it was. The big sphere has a larger moment of inertia, but it still got down the hill the same rate. It's the numerical factor in the moment of inertia. I call that the shape factor sometimes. So, like, you know how there's a 1/2 or a 2/3 or a 2/5 or a 1/3 or 1/12 in the moment of inertia all the time? Those numerical factors are the piece of information that determines it. The mass always drops out. The radius drops out. It's that shape factor only. What? Yeah. So let's start by looking at this. And so to prove that to you, we need to understand rolling motion. Okay. So it's very different than what we've been doing before. So in order to understand this, let's look at this one right here. If you were doing an energy problem, this is where it gets complicated. A ball that's rolling down the hill is both translating because it goes from point A to point B. It moves from some distance down the ramp. And then it's also spinning because it's rotating as it goes down the hill as well, right? And so if you were doing this with an energy equation, you'd have mgh 1/2 mv squared and 1/2 I omega squared. All right. Both translating and rotating. And this is what's so confusing about rolling. Now, if it's rolling with slipping, not on the test. I will show you an example later. Think about a bowling alley as it slides down the lane. It's sliding and rotating, but it could be slipping while it's rolling. We are not going to have that on the final exam, but you're going to do that as a homework problem or something, okay? This is generally covered in your dynamics class. However, if you have rolling without slipping, we know that the velocity is linked to r omega. Acceleration is linked to r alpha. The distance traveled horizontally is linked to the arc length of rotation, which is r times theta. Okay, so to be clear, we can use these equations only if rolling without slipping. We can use these equations in that scenario. That's what we're going to address in this class. Next. Now here's something crazy. Look at all this junk you've got to know. Static friction is present. However, it's usually, look, it's without slipping. If it's without slipping, do not expect to use the slipping condition. We're probably not on the verge of slipping. So generally speaking, we cannot assume F equals mu static times the normal force. Okay. Now here's where it gets even crazy. Static friction does no work. If you're not slipping, friction is required to make the thing twist. What? What? Isn't this? Oh my gosh, does this drive you crazy or what? Let me show you something here. All right. This is the road here. So let's say this thing is rolling down the road, okay? Rolling down the road. Again, the point of contact with the road is not moving relative to the road. If you're burning out your tires are moving relative to the road. If you're driving without burning out your tires are not moving relative to the road at the point of contact. This is that thing I was trying to show you where, look at the knot right here. Watch the knot. As I go towards the floor, it's moving basically straight down. As I move afterwards, it's basically going straight up. Sorry, it's hard for me to do this. Right at the bottom of the motion, the knot is reversing from nearly straight up and down motion to, or from nearly straight down to nearly straight up. Let me see if I can show you a video for this. Where is that? Sorry, I've got it here somewhere. So this is me. Whoops, I'm not sharing, am I? Let me fix that. Okay, so here I have two markers. And one of the markers is at the edge, and the other marker is right at the center. So what I'm going to do is I'm literally going to drive this wheel down the whiteboard. And what we should see is the axle at the center should form a straight line going straight across. And let's see, I can't remember which color. So let me just do this here. So I'm trying to show you a wheel as it moves. Sorry, it's not perfect. It gets pretty hard to move this thing without having it slip on you. So I had to kind of change my grip there. And so what we can do is as soon as I'm done moving this thing, I have to switch my hands very carefully. As soon as I'm done rotating this thing, we can analyze the motion as it goes up and down. Sorry if this is so boring and slow. I maybe should have sped it back up. Let me see, is there a way to... All right, so now I'm just going to skip to the end. Whoops. Okay, so now we're going to zoom in right here on this part. So this, it's kind of faint, but you can see there's a red line. Like that. This is the outer edge of the wheel. And notice right before it hits the ground, it's effectively going straight down. Right afterwards, it's effectively going straight up. That means the velocity at the bottom is 0. And this is what's weird. When you're rolling, you have forward motion and you have backwards rotation at the bottom. So the forward motion of the center of mass plus the backwards rotation of the wheel at the bottom cancel out and give you no speed of the wheel. I can't spend all day on this, so that's all I got for you. But any questions before we go on? Okay, whoops. So just try, that is purely to prove to you that the static friction applies at the bottom. I can use static friction at the bottom because the bottom of the wheel is not moving relative to the road. It does no work because it's not moving relative to the road. There's no displacement. The center of mass can be used as an axis, or look at how long bullet, oh my gosh. The point of contact could also be used as the pivot point. This is a special math trick called the instantaneous pivot. If you think about it, it looks like this. Imagine the road was made up of a bunch of pivots instead of a flat surface. And so just imagine this is like your roadway. The idea is your wheel could pivot from this one over to there. Then you get a new pivot. It pivots over to here. Then it pivots over to here. Then it pivots over to here. And you could actually view this, as crazy as it sounds, you could view an object rolling as swinging about the point of contact with the road. Trip out on that. I hope you dosed up with LSD before class. If not, it's too late. That's a joke. All right. It's never too late. Whatever. What is it? Silicon Valley? Always microdosing with the LSD these days. All right, whatever. Okay, so it's 2:01. We got to figure this out. All right, so you're going to want to reread this page later, but just rolling friction, we're going to ignore that. Sliding friction, right? We need to have static friction. It does no work, so that's great. And a yo-yo falling down a string is exactly the same kind of thing. All right? I know this seems a little bit crazy, but look at this. If I viewed this as a yo-yo, it's rolling down the string, right? So imagine there's a string wrapped around this. You're rolling down the string. Or here. When I let go of this thing, this flashlight here, sorry if I can get the angle right, it's going to unravel. And basically you could view the string as the road and it's unraveling. And you could see this pivot point here. Whoops. There we go. All right. Let's look at a problem really quick. This is our last topic. I've been saving this for last. All right. So just know that yo-yo problems basically are the same kind of thing. All right. So here's that rolling race. Mass doesn't affect it. Radius doesn't affect it. Let's show you how this one works. And I'm going to go to the solutions for 10.59, but let's take a second to read it. So I'll finish by going to the solutions, but let's start it on the board. So take a second to read that. Okay, got a spherical object here. What's one force acting on it?
mg.
Where's it act?
Center.
mg. What's another force? I need a bigger picture. Start thinking about the forces. I'm going to draw a bigger picture here. There's the ramp. Okay. Got some angle theta down there. Okay. mg acts right at the center of this thing. Hopefully that's about at the center. It's kind of hard to see from here. It's not very circular. We'll say that's the center. What's another force acting on this thing? Somebody else.
I forget the name, but is it the R pointing up?
R? You mean the reaction force at the pivot?
Thank you.
Yeah, but this doesn't have a pivot point in that sense. There's no screw, right? This is a ball rolling down a hill. In all those videos, there was no, right?
Yes, correct.
So there's
a normal force.
Normal force is present. That's the force that's kind of holding this thing from falling down, right? Which way does that point?
It's like at an angle to the right.
Yeah. So do you think it points at the center of mass or somewhere else? Turns out it points directly at the center of mass, right? This is right because there should be a radius drawn from the point of contact directly to there. All right. Any other forces acting on this?
Friction
Friction. Which way?
to the left or up the plane.
Up the plane. Okay. Where does it act? At the center? At the center or somewhere else?
Where it touches the plane.
At the point of contact. Okay. So this is sloppy here, but there's friction this way. There's our forces. Now, let me ask you here. There are two possible choices of pivot points. One is you could view it as a pivot point about the center. So you could do a center of mass pivot. If we use the center of mass as the pivot, which forces cause no torque?
Normal force and mg.
Yeah, because line of action through pivot. So the frictional force is what causes the torque that makes this thing rotate. However, there's a special thing we could do. We could actually call this the instantaneous pivot. That's what I was saying just a minute ago about this thing swinging down the roadway, about this pivot that keeps changing locations. At any one instant, you could view the point of contact with the road as a pivot. If this is the pivot, which forces cause no torque?
Friction and normal force.
Yes. And so this turns out to be very convenient because it's not that easy to figure out the frictional force. We'd have to do a full FBD, whereas this one, it's actually very easy to figure out the torque due to mg. I know the radius. I see this angle is theta. Because I drew a skinny triangle, you could bet your ass this angle's probably theta, right? And so we could actually do the torque. If I draw this a little bit better so that you could see it. This angle inside is going to turn out to be theta, because if that's theta, you could do this angle's theta. That makes this 90 minus theta. That makes this 90 minus theta, which makes this theta, or whatever you want to do to get there. It actually works out that this is theta. So, okay, let's go to the solutions because we're running out of time. We've got 7 minutes or so. This is a very cool problem. You can see I put a lot of love into these problems, people, because I know they're hard. So I tried to give you extra love here. Oh, man. Oh, all right. Whew. Somewhere, where the heck is this problem? They all look about the same, right? But you'll see. You could do this. Oh, my gosh. This is still those same problems. All right, here we go. Oh, notice I did this one 3 different styles here, right? I used the instantaneous pivot, I used the center of mass pivot, and I used energy and kinematics. So I did this in all 3 different ways for you. So this is our last problem of the day. Let's dig into here. If you use the center of mass as the pivot, N and mg cause no torque, so it's just sum of torques is friction times the radius, because, right, the distance is the radius, right? The lever arm is R, or you could say this is 90 degrees. So this is the torque due to friction. I alpha is sum of torques equals I alpha. Now, unfortunately, we don't know F. We don't know it's on the verge of slipping. We can't use mu kinetic because it's not moving. We can't use mu static because we don't know it's slipping. So you solve the force equation for friction and shove it in. Okay. When you do that, you get this big ugly equation here. And we could get alpha, or once you have alpha, we could do anything we want. Okay. You could group the 2 alpha terms and figure out that. You could get acceleration if you want. So far, so good for this method. Any questions about that? Okay. You guys are probably cooked. If we use the instantaneous pivot, this is the torque equation. Now, wait a minute. How is this going to match up? Look at these 2 equations, right? Give me a second. Compare this equation to this equation. They look totally different. How are these going to get the same answer? Parallel axis theorem. If you're not groaning right now, you're not a human being. This is tough stuff. It's all easy steps, but look, if we use the pivot point here, the distance from the pivot point to the center of mass is the radius. So notice the moment of inertia about the center of mass can't be used in the instantaneous pivot equation. This one's a lot easier if you remember that, and remember the moment of inertia needs to be shifted. Then it's just solve for alpha. It's a one-liner. Or you could use energy and kinematics. So here's the energy problem up here. Sorry, I did them in weird order here. mgh, 1/2 mv squared. Well, the height when you're on an incline is L sine theta. Remember that? When you're on an incline, if your length of your ramp is L and your angle is theta, the height is equal to L sine theta. Take a second to verify that in your mind. That's an old chapter 8 trick to get this piece. Notice omega squared, I'm going to convert to v squared over r squared again. That way I could get v. You could have also said this is omega squared r squared. That would also work. And if you go back to chapter 2, we used these answers in problem 2.16 or something? Let me see if I could find it really quick. I got it for you. We use this in problem 2.5. So we use these answers in problem 2.5. Now you know where they came from. And this is what I wanted to show you. Look at the speed of these. Notice that mass does not appear in any of them. Notice that radius does not appear in any of them. Do you see that? The mass appears in the moment of inertia and they all cancel out. The radius appears in conjunction with the moment of inertia. Mass and radius drop out. Crazy! The final speeds depend only on that numerical factor in the moments of inertia for this problem. Whoa. Whoa. This problem is so juicy, it merits you going over it again and kind of rereading this. I've just given you the highlights here. What did we see here? The shape factor, the numerical factor in the moment of inertia, determines what goes down the hill. We also saw you could use energy or kinematics for this one. You could use energy or kinematics for Pulley problems, but you can't use kinematics for pendulums. Let's just write down everything we learned today, all right? Let's just do a hardcore summary, right? Okay. So, swinging object, use energy first. Avoid kinematics because alpha is not constant. That was a big thing we learned today for the swinging pendulums. If speed, how about I say it this way? If want V or omega, try energy. That was a takeaway we learned today. If want A or alpha, try torque and force. If rolling or pulley problem, kinematics, okay, as long as no slipping. Now, to be honest, I'm not going to try to stick slipping on there. So for this class, you could just say rolling or pulley problems, okay to use kinematics. Just if you're an engineer later on, don't say I didn't tell you otherwise and say, you never told us it would change. Okay, whatever. Enough on that. Let's see. Anything else you guys can think of that we could summarize here? Oh, watch out for pulley with different radii, right? If the two radii aren't equal, watch out. And then one last thing, instantaneous pivot is important to learn about. You should learn about the instantaneous pivot. And the solutions are I believe, pretty well developed here because I've seen students struggle so much. If you get to the point where you're like, this is the same old crap, that's a sign you know what you're doing. But if you're still struggling to follow the solutions on your third problem, it's still worth doing the third problem. Only you know how much to do. So, yeah. That's about it. But I do want to point out, I went into a bunch more conversations about this that I said a lot of words. So you have to decide if you want to read this or not. This stuff talks about the math. So if you're one of those people that drives you crazy and you have a hard time doing the problems unless you understand it, that's what this is about. If you are the kind of person that can just say, look, he told me to use these techniques, then I'm going to use those techniques. Then you don't need this crap. But just be aware it's all in there. Oh, man. And the yo-yo, woo. You could do the yo-yo problems later. Oh, man, this is such a cool demo. But we'll call that there. Oh, man, there's a good one. You could redo the ball one when it's rolling. Oh, yeah, there's some good stuff here. Oh, this one. If you really want to get out there, try that problem, 67. And here's the one that says rolling with slipping. This is the one that I'm saying is not on your final. So if you want to understand what happens when it is slipping, then you could do this problem. All right. Oh, there's some hard problems in here. Whoa, woof, woof. Yowza. Yowza isn't. If you're a physicist or a mechanical engineer, those last problems, you'll learn a lot. Let's leave it at that. I'm going to stop the live stream here. And so we'll probably have a shortened class tomorrow, just so you know, because